And we're live. Well, hi everyone. Welcome to another open evening coming to you from Cambridge University Astronomy. This week, I'm very happy to say that we have some observing for you again. It's cleared 2 weeks in a row, which seems like a minor miracle at this point. So our observers are very cold out in the freezing temperatures, but that means the skies are beautifully clear. Cold temperatures mean nicely clear skies. So after our talk, we're going to have some observing for you provided by the Cambridge Astronomical Association. Before that, I'm going to be your speaker tonight. I'm going to be telling you all about colliding black holes and gravitational waves. I will say, as I'm doing my talk, if you have a question, please pop it down here in the chat over the left-hand side, which lots of you have found already. And towards the end, I'll answer as many of your questions as I possibly can. So I'm going to switch over to my talk. And begin. Okay, so like I said, today is all about gravitational waves and colliding black holes. Gravitational waves are a very, very new field of astronomy that is right on the cutting edge of what is possible to do. And it's an interesting step in the evolution of astronomy as a whole, because astronomy is a very old science. Right, astronomy was the first science. As soon as people stepped away from their campfires and looked up into the heavens and started wondering about the night sky, that was the beginning of astronomy as we know it. And all the astronomy we do nowadays, and all the things that we've learned about our universe, is just a natural progression from those first stargazers. Of course, along with being a natural progression, there have been a few improvements along the way, and I think you can really list the number of big revolutions that there've been in our ability to observe the universe. The first real revolution, I think, was the invention of telescopes about 400 years ago. So from antiquity all the way for thousands and thousands of years up until about 400 years ago, telescopes were, so we just did astronomy by using our eyes. The invention of telescopes around 400 years ago allowed us to see things that we could never see before. This is Galileo presenting his design of the telescope to the leader of Venice at the time. The invention of the telescope, like I said, it was a complete revolution in astronomy. We went from seeing with our eyes to seeing things that were completely hidden before that, like hills and valleys on the moon, and sunspots and stars in our Milky Way, and all kinds of amazing things, the moons of Jupiter. It really was a revolution in astronomy that took us deeper than ever before into the universe. So the invention of telescopes was very important. I think the second revolution, you could argue, was the ability to see beyond the optical. So from antiquity all the way up to about 100 years ago, and this includes the invention of telescopes, we were only looking at the universe with light we can see with our eyes. And anyone that remembers the electromagnetic spectrum hanging on the wall of their school physics classroom will remember that the visual part of the spectrum that we can see is this tiny, tiny part of all the energy that's out there. And so the ability to see the universe in wavelengths other than just the ones we could see with our eyes was, again, this enormous revolution. Like I said, it started about 100 years ago with this guy, Karl Jansky, who's generally thought of as the father of radio astronomy. He used this rather bizarre looking device to detect radio waves coming from our galactic center. And ever since then, astronomy has gone just completely multi-wavelength. We use the entire electromagnetic spectrum to study the sky. We found all kinds of completely hidden objects that we had no idea existed before this revolution, like pulsars, for example. We've learned about the black holes in the center of galaxies. These are some images taken in the infrared by the Spitzer telescope. Modern astronomy is a completely multi-wavelength business. You couldn't do any modern astronomy without taking advantage of this huge wealth of information. So I think the ability to access this was the second big revolution in astronomy. And I'm going to argue that the third big revolution in astronomy happened on the 14th of September 2015. And you can say precisely it happened about 4:50 in the morning. So this is when we detected our first ever gravitational wave. Gravitational waves were and are a completely new way to view the universe. We can see things that we have never been able to see before. It's opening new windows into our cosmos that, again, just like the two revolutions before it, are going to completely transform the way we understand our universe. And so that's what I want to talk about today. I want to talk about how this discovery happened. I want to talk about some of the events leading up to it and what we discovered and what that means for the very, very exciting future of gravitational wave science. So to kick things off, if we're going to be talking about gravitational waves, we need to answer the question first: what is gravity? Like, how is it possible to have a wave made of gravity? I think most people have heard of gravity and have a basic understanding of gravity, how gravity works, right? The reason we're all not floating up to the ceiling is because we are experiencing the Earth's gravitational pull. Gravity keeps the Earth the moon orbiting around the Earth and all the planets in orbit around the sun. It's the force that we're most familiar with in our everyday lives. To some extent, it holds our entire world together. The person whose name is most associated with gravity is probably Isaac Newton. He came up with the first good mathematical description of how gravity actually works. And there's this really nice story that he saw a falling apple and had this brainwave that explained gravity. And it's kind of surprised. I was slightly surprised to find out that this anecdote is probably true, right? These often these little neat little stories turn out to be just a bit apocryphal, but apparently this is true. Newton wrote a letter to his friend saying he saw a falling apple and that made him think about gravity. And he had this wonderful brainwave. It's honestly one of the best ideas that anyone has ever had, that things like apples falling and the moon orbiting the Earth and the Earth going around the sun can all be explained by one simple thing, which is gravity. And he wrote the equation for gravity down on a single line. It's a completely remarkable achievement. What he wasn't able to do, though, was explain what gravity actually is. So he described gravity as a force which pulls things together. But that description of a force that pulls things together kind of papers over quite a complex idea that he was never able to explain. How does gravity actually pull things at a distance, right? How does the Earth somehow reach out and, pull the apple down from the tree? He was never able to explain this. He described how gravity worked. He went to his grave not understanding and admitting that he didn't understand what gravity actually was. Nowadays, we do understand much better what gravity really is. And the first thing we have to say in this explanation is we have to throw away this idea of gravity being a force which pulls things together. In fact, in a modern understanding of gravity, gravity is not a force at all, which probably sounds quite bizarre to a lot of people because we talk about the force of gravity all the time. The best way to describe it is to do a thought experiment. Okay, so we're going to forget gravity for a moment, and we're just going to look at these two ants walking along a field, and it's a blue field for some reason. So these ants are out for a walk, and they're walking in just nice straight lines. And they will happily walk in nice straight lines all day until one of the ants comes across a heavy rock or something which is causing a depression, a divot in the field. If you're far away from this depression, you'd be absolutely fine. But the ant that's kind of close to this rock is going to kind of get its path deflected by the wonky ground. If it was a talking ant, it might even say something like, "Hey, that rock just pulled me towards it, right? I was just happily walking along the field, and then I felt myself being pulled towards that rock." The ants would be able to notice that if they go near this rock, their nice straight paths along the flat field get deflected by the curvy grounds that the rock is causing. If it's an especially intelligent talking ant, it might even come up with a scientific hypothesis, right? That rocks magically pull ants towards them in some way. And they might describe this as a force that rocks pull on ants. Of course, we know it's not true, right? What's going on is that because the ant's eye view is kind of limited and they're trapped on the ground, they can't see the fact that the ground is curving, and they have to come up with this explanation that the rock is pulling them. From our kind of human point of view, being able to see the whole situation, we know that there's no pulling force. It's just the ant is trying to walk straight on curvy ground. And in fact, that's exactly what's going on, right? The rock isn't pulling a force. The rock is simply bending the surface that the ants walk on. And the ants are doing their best to walk in straight lines, but the floor is wonky, which is deflecting their path. And this is basically what gravity is. You can replace the rock with the Earth and replace the ant with a satellite and say that the reason a satellite orbits around the Earth, or indeed the reason that we are all held to the ground right now, or the reason the Earth orbits the sun, is because we are living in curved space, right? The Earth isn't pulling us down with a force, it's just we are sitting in this bendy space, just like the ants walking around the rock, and we interpret this bendy space as gravity. So this is what gravity actually is. It's space being a bit bendy and curvy. So once you accept this idea of gravity, that space is bendy and curvy, gravitational waves seem kind of easier to understand. This bendy curvy space is a way of describing the theory of general relativity invented by this guy, Albert Einstein. It's one of the most famous scientific theories of all time. And Einstein's theory of relativity is a set of equations which describe the universe as being full of this bendy, stretchy space, which explains what gravity is. And as soon as you understand that space can be bendy and stretchy, it makes perfect sense that you could create waves out of it, right? If you imagine space being like a trampoline or a rubber sheet or something, it's possible to imagine kind of jumping up and down or wobbling something around on that rubber sheet and setting up waves in this bendy, curvy material. So gravitational waves are a prediction that comes straight from the equations of general relativity. You write down the equations for how this bendy gravity works, and gravitational waves are a direct prediction, right? That this bendy curvy space should form together in the form of great waves of space-time that travel through the universe. Interestingly, so after this, the theory of general relativity was published, there was a very, very prominent scientist, one of the world's most famous scientists, who was very skeptical about the possible existence of gravitational waves. That was this guy, Albert Einstein, who came up with the theory himself. So for years, Einstein was one of the world's leading gravitational waves skeptics. He wrote a paper in 1936 saying, together with a young collaborator, I've arrived at the interesting result that gravitational waves do not exist. What was going on was that he made a mistake in his mathematics. And when someone pointed out this mistake, he was a very good scientist and admitted that he was wrong and changed his mind and accepted that gravitational waves do actually exist. So yes, even Einstein can make mistakes. And so nowadays, we know that gravitational waves are a prediction of his theory. Okay, so this is way back around 100 years ago, right? So once we accept that gravitational waves can exist in theory, the next thing to do is to try to detect them for real. It might surprise you to learn that the first announcement that we had detected gravitational waves was back in the 1960s. So to describe how we're going to detect gravitational waves, I want to first describe the effect that a gravitational wave would have on an object. So as gravitational waves wash through the universe, what they do is they bend space-time, and that means they kind of bend and flex all the things living inside space-time, which is us and the objects in the universe. So as gravitational waves pass through objects, what they're going to do is kind of bend and squash and squish them. So if we take this apple, for example, if a gravitational wave passed over this apple, what it's going to do is kind of stretch it and then squash it and then stretch it and then squash it and then make it do kind of this kind of motion backwards and forwards. For reference, if the apple is doing this kind of motion, that would mean the gravitational wave is coming out of your screen towards you, right? And then this would cause this object to do this. And so in theory, this is how we detect gravitational waves. We would look for objects kind of bending and squashing as the gravitational wave passes over them. The problem with that, of course, is that how do you measure that? If you get a ruler or some kind of measuring device and try to measure an object, as the gravitational wave passes over, it's going to bend and squash and stretch your measuring device in exactly the same way as your object. So you can't just do something simple like measuring with a ruler. You need to be a bit more clever. One of the first serious gravitational wave detection attempts was made by this guy who's called Joseph Weber back in the 60s. So Joseph Weber had this idea to build what he called Weber bars, or what have come to be known as Weber bars. And so he's building one of these Weber bars here. This is a modern day picture of one of his Weber bars. It's basically just a massive cylinder of aluminium that weighs about 6 tons. And the idea is that a gravitational wave passing through the universe would pass over one of these Weber bars and then kind of make it resonate a bit like a wind chime or something. The idea of making them so heavy was that they couldn't be they couldn't be knocked or resonated by any tiny things like kind of air molecules hitting into them or something like that, because they're just too heavy to be moved by something like that. And so he basically set up lots of these Weber bars and then put these little detectors around them that would notice any movement, basically like the world's most sensitive game of operation, and waited for the bar to kind of hit one of his detectors, and that would be evidence of a gravitational wave passing over. The effect that he was looking for, that his bars would be able to detect, was unbelievably minuscule. So his bars were looking for a change in size, a kind of a stretching and a squashing of about 0.0000016 meters. This is much, much smaller than an atom. So this very, very, very tiny effect that he was looking for. Nevertheless, he said that he found something. So this was in April 1969. He published this paper called Evidence for Discovery of Gravitational Radiation. And if you look at the abstract, the first bit of the paper, it kind of speaks for itself. It says he's found things consistent with the conclusion that the detectors are being excited by gravitational radiation. And the world kind of went wild for the results. He became headline news. NASA commissioned him to put an instrument on the moon to detect gravitational waves in the very nice, clean, quiet environment of the moon. Unfortunately, things started to unravel fairly quickly. So Weber had detected these gravitational waves, or so he said, coming from the center of the Milky Way galaxy, which made perfect sense, right? There's a supermassive black hole in the center of the Milky Way galaxy, which is an excellent candidate for something that would produce gravitational waves. The problem is, when you did a back of the envelope calculation and worked out how much energy was contained in these waves, it was just a catastrophically enormous amount of energy coming from the center of our galaxy. In fact, it was enough that if our galaxy was leaking this much energy, the entire Milky Way would just be destabilized in a very short amount of time. So that was slightly suspicious. What was even more suspicious was that he claimed to be detecting his gravitational wave signal every 24 hours as the Milky Way center passed overhead. But gravitational waves can pass through the Earth very easily, so he really should have been detecting his signal every 12 hours, right, when the galactic center was overhead, and then again 12 hours later when he was on the exact other side of the world. But apparently the signal he was reporting was every 24 hours. So things started to get more and more fishy with this result. And the final nail in the coffin was really when other scientists built replicas of his machines to try and vindicate and replicate his results, and saw absolutely nothing. So I still think, so what is clear is that he was not detecting gravitational waves. I think it's never been clear whether he was committing deliberate scientific fraud or whether he was just being a bit over optimistic, because remember, he was looking for this unbelievably tiny result. So maybe he was just being a bit over optimistic and seeing something that wasn't there. That's not clear. What is clear is that he was not seeing gravitational waves. So we have to jump forward to the 21st century until we see a detection of gravitational waves. So I talked about Weber bars, this way of detecting gravitational waves by building these massive cylinders and waiting for them to resonate from a passing gravitational wave. What you actually need, and the way we eventually detected gravitational waves, you just need three basic things. You need a very long corridor, and you need a light source, and you need a clock to do timing. And the idea is that your light source will send a beam of light down the end, and it will reflect off a mirror and then come back, and then you measure the time it took to take that journey. Of course, a gravitational wave might come along and compress your corridor, but because the speed of light is constant, your light will take a shorter amount of time to go down a shorter corridor. And so that's something you'll be able to measure. And so this was a way to actually detect a gravitational wave. Of course, the amount that a gravitational wave would squish a long corridor is a phenomenally tiny amount. I'll talk about exactly how tiny in a minute, but it's too small an amount to actually use a stopwatch and time it. So instead, the technique that was eventually used was to use two corridors in an L-shaped machine. And then you take a light source and then you shine a beam of light down the arms of this L-shaped machine. Then they reflect off mirrors at the end and then come back, and they're combined back at the center in a way that lets us detect any kind of gravitational wave passing over. So this is a photo from the air of the actual machine that was used. This is LIGO, one in America. And so you can see in the middle, that's the kind of base camp where all the machinery is. And these two long spindly arms are those two long corridors, about 4 kilometers long. And the light source was sent out from the middle, went all the way down this corridor, bounced off mirrors at the ends, and came back to be combined. And it's the combining where the real magic happens. That's like the real key to finding these gravitational waves. So under normal circumstances, what happens is that one wave of light will come in from one arm, and the other wave of light will come in from the other arm. And then these two waves are combined. And under normal conditions, the setup of the instrument is that when you combine these two waves, they interfere, right? So the high bits of one wave overlap with the low bits of another wave, and this cancels the wave out, and the two waves completely disappear. So under normal circumstances, when the instrument is not being bombarded with gravitational waves, everything is tuned so perfectly, so the two returning light waves interfere to nothingness. But what happens when a gravitational wave passes? So this squashing effect is going to shorten one arm and lengthen another arm. And so that means one of the light beams is going to be delayed coming back. And so these two things are not going to arrive at exactly the same time anymore, because the gravitational wave has distorted the equipment. And so when one light beam arrives and another light beam arrives, one light beam is going to be shifted just a little bit. And so when you try and combine them, this beautiful kind of interference cancellation trick doesn't work anymore. And so the light doesn't cancel down to nothing. And so this is something you can actually see, right? So when there's no gravitational wave passing, interference cancels all the light to nothing. When a gravitational wave passes, it delays and accelerates some of the light, and you end up seeing some light, and that's something that you can detect. So the amount of shortening that this machine has to be sensitive to is hard to put into words. So a passing gravitational wave is going to distort the arms of LIGO. These are 4 kilometers long, by about 1,000th of the diameter of a proton. That's the amount that the arm is going to get longer or shorter, right? So I kind of exaggerated for cartoon effects what would happen, but in reality, this 4-kilometer arm would get shorter by 1/1000th of the diameter of a proton. And being able to measure a distance change this small, you need the same accuracy as you would need to measure the distance to a nearby star to within the width of a human hair, which it's impossible to imagine that level of accuracy, right? This is by far the most precise and accurate instrument that the human race has ever built. In fact, because this is such a fine instrument to be able to make, it's easily to be fooled by a false signal. So anything from someone kind of jumping to a truck hitting the brakes 10 miles away could cause an effect that you might interpret as a gravitational wave. So in order not to be fooled, there are many gravitational wave stations all the way over the world. So LIGO, the one I'm talking about, there's one station in Louisiana and then one station up in Washington State, both in the US. And the deal is that these both have to record a gravitational wave for us to believe that it's real. So a gravitational wave will pass by the Earth, and when it pings both stations, then astronomers can think, okay, great, we probably have a gravitational wave going on here. So the timeline of this instrument, so LIGO, like I said, is the instrument that detected the first gravitational wave. It was first built back in 2002, and it didn't see anything. It was then torn down and rebuilt and upgraded as enhanced LIGO in 2009, and again, didn't see anything. And then it was again rebuilt in 2015 as advanced LIGO, so getting more and more and more sensitive every time. And advanced LIGO was ready to go on Sunday, the 13th of September, 2015. And you can actually read interviews with the engineers and the scientists that worked on this. So they stayed late into the night on Sunday, kind of tinkering and making it ready to go. And then they switched it on, and then they went home. At 4:50 a.m. the next morning, after this machine had been switched on, LIGO detected its first gravitational wave. So this is what it actually detected. This is the raw data showing you the detection from LIGO. So in both of these graphs, time goes left to right. The left-hand one is the image from the Washington station. The right-hand one is from the Louisiana station. The up and down axis is the actual kind of stretching and squashing of the arms due to this passing gravitational wave. So this was a huge moment, right? The first time we had ever definitively detected a gravitational wave. The Nobel Prize in Physics was awarded to some of the people that were involved. And the nice thing was that this detection is so good that we were able to actually learn quite a lot about what caused these gravitational waves. So here I'm showing you the actual data from the instruments, right? This kind of vibrating line is recording these arms stretching and squashing as the gravitational wave washes over the Earth. And what scientists did was go back to the equations of general relativity and work out exactly what would cause a gravitational wave that looked like this. So they ran all different kind of things through their simulations, crashing neutron stars and spinning white dwarfs and exploding white dwarfs and colliding black holes. And in the end, they were able to make a match. So at the bottom here, we have the simulation data, right? So they look very similar. At the top, it's the real signal. At the bottom, it's the theoretical signal that we would get if two black holes collided. And of course, they look very similar because they were meant to look very similar, right? A lot of time and effort went into reproducing this signal using the equations of general relativity. And in fact, the match is so good, we can actually infer all kinds of properties about the black holes that actually collided. So for example, we can know that these two black holes were about 1.5 billion light years away. We can know that one black hole was 30 times the mass of the sun and the other black hole was 35 times the mass of the sun. And we can also know that when they merge, they produce a bigger black hole, because that's what happens when black holes crash. You take two smaller black holes, they combine to make a bigger black hole. So these two black holes, 30 and 35 times the mass of the sun, combine to make this monstrous black hole about 62 times the mass of the sun. If you're mathematically inclined, you might notice something a bit bizarre here at this point. So 30 add 35 is 65, right? Not 62. So a 30 and a 35 solar mass black hole coming together to produce a 62 solar mass black hole seems a bit weird. Where did the missing 3 solar masses go? It's not a mistake and it's not a problem in the data. There are genuinely 3 missing solar masses from this situation. We can explain where they went using the most famous equation in all of science. So E equals mc squared explains where those missing solar masses go. So what E equals mc squared tells you is that energy and matter can be transferred into each other, right? So the m stands for mass and the E stands for energy, and the c stands for the speed of light. So c squared is a very big number. So in other words, E equals mc squared tells you that a very, very small amount of mass can be transformed into an enormous amount of energy. In fact, so one really good example of the power of E equals mc squared is nuclear weapons, right? So nuclear weapons are powered by turning mass, uranium, into energy. The nuclear bomb that was dropped on Hiroshima converted about 0.7 grams of matter into pure energy. So about a paperclip's worth of matter, E equals mc squared, into enough energy to destroy a city. So that's what I mean when I say a tiny amount of matter can produce a vast amount of energy. 0.7 grams is a nuclear bomb. So if 0.7 grams is a nuclear bomb, what's 3 times the mass of the sun being vaporized into pure energy look like? It's by far and away the most energetic, the most powerful event that the human race has ever witnessed. The final moments of this collision, if you imagine those graphs kind of going up and down, those very final moments just before the black holes actually crashed together, more energy was released in that collision than in every single star in the entire observable universe put together. It's a completely unimaginable amount of energy. But that's the amount of energy that you need to shake the fabric of the universe itself in a way that we can feel the tremors of 1.5 billion light years away. Of course, in the years since this detection, we've found many, many more gravitational waves, and we're finding more and more exciting things. One really cool one in 2017 was that we found gravitational waves from the collision of merging neutron stars. This is particularly special because this was the first gravitational wave event ever seen by conventional telescopes. As soon as astronomers in the gravitational wave teams had detected the gravitational waves, we immediately started searching the sky for what caused this signal. And it was identified as coming from the galaxy NGC 4993, which is this galaxy you see here, about 140 million light years away. And you can actually see this blob that faded away over about a course of the week. So this is the first time we had our brand new tool, gravitational waves, and regular telescopes working in tandem to be able to discover events. So gravitational wave science is very new. We discovered the first ever gravitational wave not even 6 years ago. And so there's a huge amount to come. And so there's a lot of very, very exciting stuff in the future that's going to take gravitational wave science to a whole new level and let us discover things that hopefully we've never dreamed of. One of the things that I'm really excited about is a mission called LISA. And the basic idea behind LISA is to build a gravitational wave detector on an even larger scale. So rather having 4-kilometer arms in the desert in the US, you can have these telescopes which fly thousands and thousands of, millions of miles apart in space and talk to each other with lasers. And then if they fly in formation and a gravitational wave washes through the solar system, their formation will be disrupted in a way they can measure. And so LISA is going to be able to measure and look out for gravitational waves with wavelengths of millions of miles caused by things like supermassive black holes in the center of galaxies. And so all of this is ahead of us. I think the gravitational wave future is going to be very, very exciting. Like I said at the start, I think the detection of gravitational waves is genuinely a revolution in astronomy. It's detecting the universe in an entirely new way. And every single time in the past that we have, that there's been a revolution in astronomy and we've seen the universe in a new way, we've improved our understanding, but we have also discovered things that we'd never dreamed of before, right? We discover entirely new parts of the universe. And there's no reason to think that gravitational waves are any different. It's going to improve our understanding of things we already know, but it's almost certainly going to lead to new discoveries of things that we just don't know exist. And I can't wait to see what we find. Okay, that's a good time to finish. I've been talking about for about half an hour. So what I'm going to do now is go over to your questions. So I know the observers are waiting in sub-zero temperatures, so I don't want to keep them waiting too long. I'm going to answer just a few questions if I can. I saw one at the start. I guess we'll kick off with talking about pulsar timing arrays. And so this is a prospect that we might be able to use to detect enormous gravitational waves with wavelengths measured in the thousands of light years. These gravitational waves are going to be almost impossible to detect on small scales. And by small scales, I mean the size of our entire solar system, for example. We might be able to detect these gravitational waves by using the entire galaxy as a gravitational wave detector. So the Square Kilometre Array, which is the next generation of radio telescope that's going to be ready in about 5 years or so, will be able to monitor networks of dead stars all the way through our galaxy and see the effect of galaxy-sized gravitational waves washing through the Milky Way. And so I think we're absolutely going to use these, what we call pulsar timing arrays in the future to detect some of the biggest gravitational waves of all. Gaurav says, can gravitational waves generated by colliding black holes give some clues about the fabric of space and dark energy? So I think that one at the moment will have to be, we don't really know. The answer, the problem with dark energy is that we understand very little of it, right? We see an effect, which is that the universe seems to be getting pushed apart faster and faster and faster. And we call that effect dark energy. We have very little understanding of what is actually going on and how to actually describe dark energy. And so it's very hard right now, knowing very little about what the future is going to be, about to say whether something will or will not tie into it. It's possible that that dark energy is a direct result of general relativity in the fabric of the universe, and if so, it's not unreasonable to say that understanding gravitational waves and black holes might give us clues to the underlying theory. On the other hand, it might turn out to be something completely different, and so it's really hard to know. But it's a fantastic question. It's one of those questions I would absolutely love to know the answer to. Angus asks, what's the difference between a black hole singularity and a supermassive black hole singularity? The clue's in the name, really. I think the only difference is the size. So a singularity, as far as we can tell, according to the laws of physics, is an infinitely small dot, right, with some mass attached. And a supermassive singularity is an infinitely small dot with a lot of mass attached. And a regular singularity is an infinitely small dot with a normal amount of mass attached. So we have stellar black holes that weigh, maybe the mass 10 times the mass of the sun, 20, 50, or 100 times the mass of the sun. And then we have supermassive black holes, which can weigh millions or billions of times the mass of the sun. The only difference is how much mass there is in the singularity. One Where are we? I'm going to see if I can find one more question. Um, Thomas says, would gravitational waves be stronger closer to the source? And if they are, could they disrupt objects in orbits around black holes? It's an excellent question, Thomas. It is absolutely true that gravitational waves, like any wave, are stronger the closer you get to the source. I think you would need an awful amount of loss of gravitational energy to disrupt an orbit around a supermassive black hole. So I don't totally know the answer to that. I know that we can see the effect of gravitational waves when we see the orbits of some of the things in space. So the first way we got evidence for black holes was actually, for gravitational waves, wasn't this direct method I'm talking about. We first got evidence for gravitational waves in a very indirect way, that we looked at a pair of neutron stars orbiting around each other. And theory tells us that if these neutron stars are emitting gravitational waves, that they're losing energy, and so that the orbit should be slowing down. And then we were able to measure the orbits of these neutron stars, and we saw them slowing down in exactly the way that gravitational wave theory predicted. So gravitational waves absolutely can affect orbits, and that's the first way that we detected them. But of course, seeing indirect evidence is one thing, actually detecting something for real is something else, which is why we got very excited when we detected gravitational waves directly. So I think I'm going to hand over to our observers, who are, I'm sure, shivering away in their telescopes and don't want to keep them waiting any longer. Thank you so much for all your questions. I'm sure I didn't get to all of them. I will say at this point, if you enjoyed this talk, we've got another one next week, and we're doing them all the way through March. Do consider giving our channel a subscribe if you are enjoying this stuff, because we have more talks and more fun things coming up. With that, I think I will hand you over to the Cambridge Astronomical Association. Are you ready, Brian?
Yes, thank you. Okie doke. Well, an exceptionally clear night. And first off, we're going to visit Paul's observatory at Over. What have you got for us, Paul?
Hi, Brian. I'll get my image on the screen for you in about 10 seconds. I've got the Eskimo Nebula for you. So I'm just going to turn my camera on. I've been saving the battery. It's so cold here that the battery wouldn't last otherwise. So just give me a second and we'll have it for you in as long as it takes to take the photograph.
Okay. When stars run out of nuclear fuel and die, what happens next is dependent on the size of the star. Small stars up to 8 solar masses will puff off their outer layers, and the leftovers will be white dwarf stars in a planetary nebula. But a planetary nebula is nothing to do with planets. It's just a phrase coined by William Herschel, as some of these nebulae look very similar to the then newly discovered planet Uranus. And Paul's now going to show you one of these planetary nebulae.
Yeah, just give me a second.
Okay, no worries. So this is what happens to small stars like the Earth. Bigger stars between 8 and 25 solar masses won't puff off the outer layers, they'll go supernova, and their remnants will be neutron stars. And the biggest,
here you go, Brian.
Thank you. And the biggest stars over 25 solar masses will also go supernova, but their remnants will be black holes. So there's the three groups to look at. And the Eskimo Nebula is one of the smaller ones. It was remains of a star nearly twice the mass of our sun that exhausted its fuel about 10,000 years ago and puffed off the outer layers. And as you can see, we're seeing the nebula. You can see the bright white dwarf in the center, and then round it is the face of the Eskimo, and then round that is a faint shell of the Eskimo's hood. So we're actually looking down on the spin axis of the white dwarf, and that faint outer ring was some material that was thrown off when the star was at the red giant stage of affairs. And before it turned into a white dwarf, it puffed off this shell of material, which is expanding at a fairly leisurely 25 kilometers per second, sorry. But once the white dwarf had formed, it ejected a very fast stellar wind of 1,000 kilometers a second. So the Eskimo's face is this bubble, this fast expanding bubble. But because the outer layers of the hood, the disc, was very much denser, it's constricting the bubble into a stubby sausage shape. And so we're looking down on the end of the sausage shape.
I don't know whether you can see on your screens, Brian, but I've got lovely detail in the outer ring and also the brown color at the bottom, whereas the rest of the ring is green.
Yeah, they're most planetary nebulae show these things called flyers, which stands for fast low ionization emission regions. You don't have to remember that. And we can see two. The big one at about 5 o'clock is like a beard, and then there's a smaller hat one at about 11 o'clock.
I can see them all round as a whole ring.
But we can only see the main one at 5 o'clock and possibly a hint of one at 11 o'clock. But it's just that these flyers are just fast moving gaseous blobs. And the beard is moving towards us, and the little tiny hat is the other side moving away from us. So that's very nicely picked up. I've got some superb conditions tonight. And then over thousands of years, this nebula will disperse into the interstellar medium, while the white dwarf, this very hot star, will just spend the rest of eternity cooling down. Okay, thanks, Paul. We're going to go on to David Holton and see if he's found anything.
Hello.
Hiya. How cold is it in your place?
I'm at -2 at the moment.
No, that's not too bad then. The trouble with the observers is they can't operate the computers with gloves on, so we're going to be fairly brief tonight. Right. And this is Messier 1, or M1 as we call it, the Crab Nebula. And this is the remains of a supernova that was seen to explode in 1054. The supernova was spotted by the Japanese and Chinese and Arab astronomers, and it could be seen in daylight for 23 days, and it remained visible for nearly 2 years. Of course, this was well before the invention of the telescope. And once it faded from view, people forgot about it until a doctor in Wiltshire named John Bevis picked it up in a telescope in 1731. And it was also seen by Charles Messier, who mistook it for Halley's Comet. And that's one of the reasons he created his list of objects. And it's number 1 on his objects of things not to be confused as a comet. And the remnants of this supernova can be seen expanding when photographs are compared a dozen years apart. And it's estimated that the star was about 10 solar masses before it exploded, which means it's well above the 8th solar mass threshold I talked about. and so didn't form a white dwarf, but formed a neutron star bang in the middle of the nebula. We can't quite see it, but this neutron star is twice the mass of the sun in the size of a city-sized star, a very dense star. A neutron's a white dwarf, a teaspoonful of white dwarf material weighs about 15 tons. A teaspoon of neutron star would weigh about 10 million tons. That's about nearly 20 decent-sized battleships. And the neutron star here rotates 30 times a second and is a pulsar. Pulsars are these rapidly spinning compact stars which emit beams of electromagnetic radiation from their magnetic poles. And if the beams cross our line of sight, the radiation can be detected as pulses. And the first pulsar was discovered in 1967 out at Mallard Radio Observatory on the Barton Road, where the radio telescopes are. And this pulsar in the Crab Nebula was discovered the following year by the largest radio telescope in the world. That's a 1,000 foot telescope in Arecibo in Puerto Rico. And this telescope collapsed just a couple of months ago. You can see the carnage on YouTube, a very expensive crunch. There was some cables failed and the telescope was ruined. So just look at it look up Arecibo and telescope collapse on YouTube and you can watch it happen. It's quite spectacular. But this nebula has been expanding ever since 1054 and it's now about 10 light years across. So that's good. And we can see, how long a exposure is this, David?
This is 30 seconds.
Yeah, so this is the best supernova in the northern sky, but you need superbly clear skies to see it. It's very dim in a telescope. David's having to give it quite a lengthy exposure.
This is a hydrogen alpha image.
Right, this shows some of the structure we can see there of how the outer layers of the star have are dispersing into the interstellar medium. Great. Okay, thanks, David, and we'll now go over to Mick. How you doing, Mick?
That's it. Okay, I've got M35 up on the screen.
Okay, brilliant.
I'll share my screen. I'm just going to. That's the telescope. Can you see?
It's starting to share. That's the telescope. Yeah.
That's the telescope I'm using tonight. It's the 100mm with a CMOS camera on it.
Okay.
Because everybody seems to ask every week.
Yeah.
That is 35, Brian. It's a small portion of it because the telescope isn't wide angled enough.
No, we're seeing your telescope at the moment. We need to see the image of M35, please.
Hang on.
Unlike the others, you haven't got a dome, so you just have to get very cold when you're out there.
That's it.
Right. Have you got the other galaxy, the other cluster beside it?
I'm not sure. I've been able to getting it through the telescope this evening. I've had a few problems.
Okay.
M35.
Okay. Well, we'll M35 is an open star cluster. We were hoping to show you that there was a small star cluster beside it, so you get 2 for the price of 1. But this is in the constellation of Gemini, and it's quite big, and we're seeing only the central portion of the cluster. All these big stars we're seeing are the red and blue giants in the center of the cluster. And because this cluster is less than 4,000 light years away, it means it's close enough to measure the random motions of the stars. All you do is you take a couple of photographs and separate them by 10, 20 or more years, and then you overlay them and you can see the motions of the stars. And thus you can start to work out the mass of the cluster. And the question that they were able to answer with this particular cluster was, is there any dark matter in this cluster? Well, astronomers worked out, they measured all the positions of the stars and worked out the motions due to gravity, and they added up all the masses of the stars, and the mass could be accounted for by adding up all the stellar masses. So the answer to the question, is there any dark matter in this cluster? The answer is no, not this particular cluster. So that's the sort of things you can do with open clusters. And because the stars all form the same time, you can see how stars evolve as a group. And this, there are many open clusters along the Milky Way, and sometimes binoculars are better to use than telescopes. As you can see, Mick is only seeing the center portion of all these stars. We can't see it as the cluster in its entirety. So do get a pair of binoculars out and scan along the Milky Way, and you'll see quite a few of these star clusters. Often the clusters that fit inside the telescopes are in this telescope's field of view are very much smaller and very much further away. Okie doke. Thanks, Mick.
Okay.
And then we'll go back to Paul. How you doing? We've lost Paul. Here he comes.
I've got M81 for you.
Brilliant. Right.
This is just a sighting shot. Let me share the screen.
Yeah.
Wherever it's hiding.
Now we've moved from stars to galaxies now, and M81 is, or Messier 81 is a galaxy, and this is a spiral galaxy. It's also known as Bode's galaxy after Johann Bode, who discovered it in 1774. It's a lovely spiral galaxy with 2 well-defined arms. Right.
It was just an 8-second sighting shot.
Yeah, and you're going to increase.
Just got it. I'm going for a 30-second image now, and you should be able to see it a bit better. So about 15 seconds to go. Okay.
This galaxy is slightly smaller than the Milky Way galaxy, and it's comparatively close at 12 million light years and has been well studied by astronomers. And the Hubble Space Telescope can resolve individual stars in this galaxy. Right, we should get to see it pop into view any minute.
I think that's it. The spiral arms are
Can you point them out?
here,
There's one.
down across the middle,
And oh, yeah, I can see the other one.
and up to here. It's, I'll see if I can get a better image. Carry on.
Okay, I'll carry on nattering. And the astronomers believe the structure of these spiral arms may be the result of an encounter with another galaxy. And also the gas around M81 seems to be stirred up. And it also has an active nucleus, the nucleus we could see there, which has just vanished.
Sorry, my fault.
No, don't worry.
Yes, that's a 1 second exposure because I twitched.
Don't worry. And then it'll come back. And this, at the center of that nucleus is a supermassive black hole. And it's considerably bigger than the black hole in our galaxy. It's 20 times bigger than our supermassive black hole. So although the galaxy is smaller, yeah. So that's the nucleus where a lot of the older stars are, whereas the spiral arms are often bluer, coloured by young blue stars. So whenever you look at a picture of a galaxy, obviously, if Paul had more time, he would take a longer exposure and be able to bring out the more detail. But we're pressed for time. Right, Paul, do you want to go for M82?
I will do. I'm just halfway through a longer exposure for you.
Okay, we'll just wait.
And then when that's cooked, I'll move on to the neighbouring galaxy. Which,
Okay.
Take me a couple of minutes to find it.
Okay.
Everything in the telescope and on the camera screen is upside down and backwards half the time. So it's in one of the 4 directions.
Yeah, I know what you
Do
mean.
you feel lucky?
Yeah, I think we've got to go for it. Right. How long?
It's a minute-long exposure coming now.
Okay.
I can see the spiral arms quite nicely on my screen.
Yeah, we can start to see some structure, but the spiral arms are not
I think
as clear
Zoom
as...
is editing them out a little bit.
Yeah, that's the trouble. We'll have to live with it. At least it's not turning it into a cat. That's the important thing. Okay, then. You whiz.
Okay, I'll go for the next one.
M82, also discovered by Johann Bode on the same night he discovered this spiral galaxy. But this one's going to be totally different, and hopefully we'll see some structure. Originally, it was classified as an irregular galaxy, but we now know by work done with X-ray telescopes and infrared telescopes, we can see spiral arms in M82 as well. So it's not an irregular galaxy, it's an edge-on spiral galaxy, but it's only quite a little dinky one. It's about a quarter of the size of the last of this galaxy we can see at the moment, M81. And what's happened is M82 got uncomfortably close to this spiral galaxy, and gravity triggered a burst of star formation about 100 million years ago when it passed by. And this is what we'll see.
If I can find it. Yes, I found it. There it is.
Yes, we can see it. Yes,
right at the
down
bottom there.
Right at the bottom. And you can see it's a band of galaxy. We're seeing it edge on, but right in the middle, we can see this galaxy is in trouble. You can see there's something going on in the middle. And what's happened is that large stars live fast and die young. And these large stars die as supernovae, pumping lots of energy into the core of M82. And it sort of puffs up the center of this galaxy. But since the spiral arms constrain this puffiness.
That's better.
Yeah, we can see it now, yeah. The puffiness can only escape at right angles to the plane of the galaxy. And there we can see some of the red colour of some of this disturbance. And also looks like a break in the galaxy, but that's gas and dust. And this is a starburst galaxy. And what's happening, all the cold molecular gas is being turned into these stars, which are then going into supernovae, but it can't sustain this level of star formation for very much longer. It's been going for 100 million years, and it will probably go for another 100 or 200 million years at most. And then it will have used up the gas. So all the stuff is sort of squirting out sideways from the spiral arms. And as well as creating an enormous amount of stars, because it's creating these large stars, they should be going supernova, probably one every 10 years. But so far, only one supernova has been discovered recently in 2014 by a group of students being shown how to use a telescope. One student said, 1 minute we were eating pizza and 5 minutes later we discovered a supernova. And I believe we saw this supernova when we were on the lawn of the Northumberland, on the Northumberland lawn at the Institute all those years ago. And as we saw with the Crab Nebula, once it explodes, it creates a lot of material and ejects it into interstellar space. And so from all those supernovae, there's a lot of hot gust and dust that stops us seeing all those supernovae that occur in the core. We may be able to pick them up with radio telescopes, but we won't pick up many visually. So that's why we can't see all these supernova going off, because our vision is being impaired by all this gas and dust from these supernovae, from these young massive stars that are forming. So that's the starburst galaxy. Okay, thanks, Paul. And now we'll go back to David. Now, last week we looked at the Orion Nebula, but we were hampered a bit by cloud, hazy conditions. And so we thought we'd give it another go. So how are we doing, David?
Can you see this? This is the trapezium.
Yes, that's good.
This is the whole field of view. So this is a 1 second exposure. Right.
And this is, yes, that's the trapezium. And we can see that there are 4 stars. Poor Galileo, when he first looked at it, he could only see 3 stars. But the biggest star is the one at the top, and that's over 30 solar masses. And this star has cleared out a cavity of the molecular cloud. and we're looking into this cavity. And it's a stellar nursery. These are young stars. These trapezium is probably, they're all about 2.5 million years old, so relatively young. But as I said before, large stars live fast and die young, and that big star, the top star, will probably only last 7 million years before it goes supernova. But the Hubble Space Telescope has looked into this cavity and seen about 2,800 young stars, really young stars. And now we're zooming into the cavity. Are you going to give it a longer exposure?
I'll wind it up now.
Okay, thank you. And while we won't be able to see the very young stars, we'll be able to see more structure of the Orion Nebula, M42. And the Hubble sees these young stars, but some of them are so young, they're still surrounded by gas and dust. They're sort of protoplanetary disks, and some of them, the stars, haven't even yet switched on. So this is indeed looking into a stellar nursery. And if we come back in a few million years' time, we'll see many more stars like the trapezium. Now we're starting to see the color of the Orion Nebula, and it's this lovely pinky color. And this is caused mainly by that big star. That'll do nicely. That's brilliant. Good. Mainly by the big star of the trapezium, the 30 mass one, solar mass one, exciting the gas. So the excited gas glows as this pinky color, and it's mostly hydrogen we're seeing. So it's an emission nebula, because if it was a reflection nebula, it would reflect the light of the star, which is blue. So we'd have a blue patch there. But this is just purely the gas being excited by that massive star. And the cavity we were looking into, the central little bit, is about 24 light years across. But the whole nebula we can see going out to about 40 light years. David, could you point out M43? That's this one. Again, most astronomers forget about this, but this is amazingly important. Again, it's a cavity, but it's only a couple of light years across. And again, it's being the void has been created by that bright star you can see where David's pointing to. But they were able to examine the motions of the gas within this particular field, and they found the region around M43 is actually blundering into the area where M42 is. So that's what's triggered all that star formation and the trapezium and everything. So if it wasn't for M43, the Greater Orion Nebula wouldn't be there, because as it pushed into the gas, it's compressed the gas and triggered the star formation. So that's the Orion Nebula, and we can see that again, it's a fine sight in binoculars. You can, if you've got a good pair of binoculars, it will show you the trapezium set up, and it will show you the gas clouds around M42, and if you've can hold the binoculars steady, you might be able to pick up M43 as well. And it's very easy to find. Orion's a very distinctive constellation to find, due south at the moment. And just look below the belt of Orion, the 3 stars in the belt, and in the sword, you'll see this fuzzy blob, and you can pick them up quite nicely with binoculars. We can see this in glorious colour, but unfortunately, when you look at it through a telescope, the human eye just isn't sensitive to these faint reds we're seeing. So you just see it as a misty patch in a telescope. Oh, a satellite's just gone by.
Yeah.
Well done, you picked that up. That streak is a satellite that's just across the field of view. Okay, and we're now going to head, thanks David, and we're just going to head back to Mick for our last object. How are we doing, Mick?
We're okay when
I'll stop sharing. There we go.
right, share screen. There we are. That's the M44, the beehive cluster.
Right.
Anyway.
Yes, again, we're looking at a very big cluster. This cluster is much bigger than M35 we looked at before, because it's much closer. And the only thing to look at this is with binoculars. You can see it as a faint fuzzy blob with the naked eye, and it's in the constellation of the Crab, Cancer, the Crab, which is a dismal constellation. It's very hard to see, not very many bright stars. But this cluster was one of the first objects that Galileo looked at with the newly invented telescope in 1609. Galileo's telescope had an even more limited view than Mick's telescope. And we're looking at the central portion, whereas Galileo had to look at a tiny fraction of that area. But if you look at it with binoculars, you'll see the 38 stars that that Galileo observed and drew. It's they're quite bright and easily picked up. But we're looking at the central region, which is mostly made up of red and blue giant stars. And this cluster, like many other clusters, shows mass segregation. And this happens with lots of star clusters. In a swarm of stars, their random motions mean they pass each other. And the lighter stars will pick up speed during their encounter and go to the edge of the cluster, while the heavier stars lose speed and sink to the middle. And that's why we've got all those bright stars in the center of the cluster. And it also happens with galaxies. When we look at clusters of galaxies, you tend to find the biggest galaxies are in the center of the galaxy cluster, while the smaller dwarf galaxies can be found usually around the outside. Now, this cluster came to note in 2012 when it was the first cluster when they discovered exoplanets. They found a couple of them orbiting a couple of fainter stars in this cluster. They were sun-type stars, but they were hot Jupiters. That means they orbit close and are fairly massive. And since then, the Kepler Space Telescope has discovered 4 more exoplanets in this cluster. Just some useful numbers to remember about the beehive. The beehive is relatively close, nearly 600 light years away, and it's 600 million years old, and of the 1,000 stars, it has 600 red dwarfs, which means that you don't see many of those, not in binoculars, because they're just too small to see. So we're only seeing the larger stars. Okay, it's time for us to stop. Just to say thanks to our team of observers, Paul, David and Mick, who've produced some excellent images, despite the fact their fingers must be totally numb by now. And thanks very much. And we'll hope to see things again on next Wednesday. And now I'll hand you back to Paul, to Matt. Thank you. I'll get your name right.
Thanks, Brian. Third time lucky, right?
Yeah, okay.
Yes, so thank you to Brian. Thank you, as you said, to all of the Cambridge Astronomical Association for that viewing. It's lovely to have nice crystal clear skies, even if they were freezing their fingers off. So yes, I hope you all enjoyed the talk on the stargazing. We will be back next week with a talk all about the nature of dark matter. As I said in the middle, if you did enjoy this, consider giving us a subscribe. We have these talks every Wednesday evening through the winter, as well as all kinds of exciting content coming up. And particularly, we have the Cambridge Festival coming up at the end of March. And there's going to be a whole spectrum of amazing talks, including things about black holes, things about destroying planets, and a tutorial about how to bake galaxy cakes. So we're going to have all kinds of very cool things coming up. So see you next week.
Bye.